I had version 1 and version 2. I'm thinking of, oh, where is that handout? It's not quite within reach. I'm thinking of this handout here, work energy theorem version 1 and version 2. Version 1 says, let me do it like this. Delta K is the work done by all the forces, the net force, the sum of all the forces. So in this problem, normal was 0 and gravity was positive. So in this case, this is, like normal force work and gravitational work, 0 and positive. So this is positive. This is what I called version 1. How low can I go and stay on the screen? Not too much lower. What about version 2? I'll just say version 2, which is the way it's written on that handout. And remember, sorry, what I meant to say about this handout is you can use this on the test, this handout here on the test. What is version 2? It says the change in mechanical energy is not the work done by all the forces, it's just the work done by the NC forces. And I mean that's short for non-conservative. So this is all forces. This is just non-conservative. In this case, what's the only non-conservative force? Normal. And then the third thing I would say, maybe I'll put it at the top, I don't know. What's the third key fact? By definition, change in potential energy is -1 times the work done by that force. So this is actually like the definition of potential energy. The definition of potential energy is, maybe I'll go to a darker color, delta U is -1 times the work done by the conservative force. For example, delta UG equals -1 times work G. You could also say delta U spring equals -1 times work of the spring. This is the definition of potential energy. We did the problem on Monday where we moved the block from A to B following 3 different paths, and in all cases, gravity did a negative amount of work, and that would be related to the fact that the change in PE is positive. Let's talk just briefly about the term potential energy. What do we mean when we say potential energy? We have potential energy of gravity. We have potential energy of springs. There's other types of potential energies as well. Why do we use the same term potential to name or describe several different types of energy? What do those energies have in common? If an energy depends on speed, we call it a kinetic energy. If an energy depends on the location or position of an object, we call it a potential energy. So that is kind of what potential energy really means. It would be better to call it something, I mean, the name potential is not the worst name, but it's also, I don't think, the most insightful name. It'd be probably better to call them kinetic energy and positional energy. Energy that depends on how fast you're moving, K. Energy that depends on your location or position, capital U. So that's how that one goes. I would always imagine on a question like number 1 on the handout, which doesn't have calculations involved, could you imagine taking this question and adding a couple key numbers to it and turning it into a calculation question? Right now, I would call it a conceptual question, the kind of thing I put early on in a test, page 1. Could you imagine adding some numbers to this problem and kind of promoting this question from a conceptual question on page 1 of the test to a calculation question on like page 3 of a test? If you wanted to make this a calculation question, I'm going to go back to the view and just say in the chat, what are some pieces of information that you would want to know if your job was to calculate something about the journey from A to B? Like, what decimal values would have to be provided? I suppose I would probably want to know mass of block. I'm just going to make up a number, 10 kilograms. What else would you maybe want to know about the journey from A to B? You might want to know something like distance traveled. And I'll say it, make up a number, 2.50 meters. How far is B from A? Let's say 2.50 meters. Anything else you'd want to know? If your job was to calculate the work done by normal force, calculate the work done by gravity, the change in PE of gravity, the change in KE, the change in ME, what kind of numbers would you need? Incline angle. Yeah, we need two pieces of geometry. We could be told the distance along, and then the angle. We could be told the height change in the angle, something like that. So let's say the incline angle is I think I said before 35 degrees as an example, so I'll stick with that. Okay, I think you could, with something to find y of the incline. Yeah, I think if you were given a distance and an angle, you'd be able to do enough trig to find what you need for all those questions. And you could now, with those numbers in the chat bar, go and calculate all the non-zero values that we described. However, we already figured out a couple of them are zero. So we don't have to worry about calculating those. We know it's zero. We know they're zero. What if you wanted to find the final speed? If the question was, what is the final speed of the block, or box, whatever I called it, you would need to know one more thing. You need to know, be told one more piece of information. Information. I'm trying to type it over here. Okay. If the question was, what is the final speed of the block? Now, that wasn't the question on number one. The question on number one was, what's the work? What's the change in KE? What's the change in PE? If the question is, what is the final speed of the block, which is very often the kind of question we're trying to address using energy conservation, energy principles, you would need to know one more piece of information. What else would you need to know to figure out how fast the block is going at the bottom of the hill? Told something about V naught. Yeah, we would need to, if you want to know if you want me to find a final speed, I gotta be told the initial speed. So let's just say initial speed, like at point A, which you could call VA or you could call V0, V naught. Let's say the initial speed at A is just 1.4 meters per second. So I think now between the mass of the block, the distance traveled along, I interpreted 2.5 to be distance along the incline from A to B, inclination angle 35 degrees, initial speed is at A is 1.4. Then we could find the final speed. And of course, to find the final speed, the key issue would be, let's find the change in kinetic energy. Okay. So, you know me, I'm very big on understanding signs. I'm very big on understanding increase versus decrease before worrying about getting too in depth on the decimal calculations. Okay, so we're going to go to the screen share and we're going to do the second problem, which has numbers in it pretty fully. I'll maybe gesture to the board a little bit as we go. So let's move up here. I'll read the question right here. I think the diagram describes the question pretty well. The two blocks are positioned as shown with the masses as shown, and they are released from rest. The key question is part D. How fast will the heavy crate be moving when it hits the floor? I'll read it now. A 15 kilogram crate and a 20 kilogram crate are attached via a pulley system. The light crate is positioned 1.2 meters above the floor, heavy crate 1.80 meters above the floor as shown. The crates are then, here's a key phrase, released from rest. So what are the initial speeds? What are the V knots? 0 for both crates. And the heavy crate drops and hits the floor. Ignore air resistance. The other thing I probably should have said in there is, assume the pulleys are massless and frictionless and the rope is massless. All of our standard assumptions that we would put into like a nice idealized version of a pulley question or a rope question. Let's just build this up one by one. What's the initial potential energy of the 2 crate system? The key to this problem is the hint. We're going to do conservation of energy, but we are not going to do conservation of energy for just this object or just this object. We're going to do conservation of energy for the 2 of them combined. So let me see. Easiest question on the board. I'm going to write it out here. Easiest question we could ask ourselves, what is the initial kinetic energy of the system? This guy's at rest with 0. This guy's at rest with 0. 0 plus 0 is 0. So the initial KE is 0. I'm going to use this general principle here. I'm going to use this general principle here. K initial plus UG initial equals K final plus UG final. But for each of these, there's 2 terms here, there's 2 terms here, there's 2 terms here, and there's 2 terms here. Because I have 2 objects changing height, I need to keep track of their PEs. I have 2 objects that are changing speed, I need to keep track of their KEs. So this is conservation of energy. When do I get to do conservation of energy? If the work done by the non-conservative forces on the system is 0, then I can do conservation of mechanical energy. And I'm just going to say that that is true for this problem because it said no air resistance and stuff like that. So I'm going to now expand this out. It's going to be twice as many terms. K1 initial, K2 initial, and object one is going to be the lightweight block, and object 2 is going to be the heavy block. UG1 initial, I'm not going to write the G's, but all the potential energies are gravity. UG2 initial, K1 final, K2 final, U1 final, U2 final. These 4 terms add up to these 4 terms, conservation of energy. Okay, let's just start going through them. This is going to speed up. Now, here's my hope. Ready? My hope is that some of these terms are 0. I hope I don't have actually 8 different numbers to keep track of, but if I do, I do. This guy is at rest, and this guy is at rest. So they're both 0. We know the initial heights. This guy is 15 kilograms, and he starts out at height 1.2. So we can just calculate, potential energy is mgy. So I'm going to do, 15 kilograms times 9.80 times 1.20. This guy starts out with is that on the screen? Yeah. 176.4 joules of potential energy. Somebody had to lift the lightweight crate up this high, and to lift the lightweight crate up that high pumped energy into the system. Number 2 is heavier. Number 2 is 20 kilograms, and he's at a higher height, so he has 352.8 joules. And together, that is the total potential energy of the system at the start, and that's part A of the question, and whatever those add up to, they add up to. And 529 joules, 529.2 joules. Might be off the screen, I don't know. Really easy is what are the initial KEs? 0 plus 0 for a total of 0 joules. Excellent. We're done with the initial state. We've said kind of everything there is to say about the initial state. Oh, just a little bit too high. Right there. I don't know if you can see that. Okay. Let's go to the final state. I'm going to scroll down, scroll down, scroll down, scroll down. Here you see worked out the 176.4, the 352.8, adding up to 529. I said in parentheses over here, initial kinetic energy is 0. Okay, now I'm going to go back up to this one here. What height will the 20 kilogram crate end up at? He's heavier than 15. He's going to fall and hit the ground. So his final height is 0. What's his final potential energy? His final potential energy is 0. Can you see that on the whiteboard, perhaps? So how many terms did I have at the start? 4 on the left, 4 on the right. 2 of them on the left are 0 because they're not moving at the start. 1 of them on the right is 0 because it ends at ground level. The other 5 are all non-zero. Didn't start on the ground, didn't start on the ground. The second crate is not going to end up on the ground, so that's not 0. The final crate, the first crate is moving at the end, the second crate's moving at the end. Where will the lightweight crate end up? I have to do mg, I have to do 15 kilograms times 9.8 meters per second squared times final height of lightweight crate. What's the final height of the lightweight crate? He started out 1.2 meters off the ground, and the other crate descended 1.8 meters, so this guy's going to rise 1.8 meters. So he is going to actually gain potential energy because he's going up. So I'm going to redo this. Final height is 3 meters, and just do 15 kilograms. I think it's written right in here somewhere. Here's the first crate, 15 kilograms, 9.8. Final height is 1.2 plus 1.8. And that comes out to be 441.0. So this one is 441 joules plus 0 joules. And what about the heavy crate? It went down 1.8 and ended up at 0. Okay. What happened to the potential energy of the system? 529.2, where the crate started, and when the heavy one went down and the light one went up, the total potential energy at the end is 441. So what happened to that contribution? Increase, decrease, or stay the same? It decreased. However much blue decreased on the whiteboard, that's how much the kinetic energies have to increase because we think that kinetic plus potential is conserved. So if you set up conservation of energy, you find that here's what you get. The kinetic energy of the potential energy went down 88.2 joules. And so the kinetic energy increases 88.2 joules. It started at 0, so if it increased 88.2, the final kinetic energy of the system is 88.2 joules. And that, I think, might be part C right here. Part C, what's the final KE of the system? 88.2. Part D, how fast will the heavy crate be moving when it hits the floor? How do I use the 88.2 joules to figure out final velocity? Erase some numbers here. So here's what I've got so far. Here's what I've got so far. Final kinetic energy of the system is 88.2 joules. What does that equal to? That's equal to the kinetic energy of object 1 plus the kinetic energy of object 2. So that is 1/2 15 kilograms times V1 final squared plus 1/2 20 kilograms times V2 final squared. How do the final velocities compare? They're connected by a rope. Every time the heavy block moves down 10 centimeters, the lightweight block moves up 10 centimeters. So you could either say they're the same velocity, you could say they're the same speed, or you could say they're opposite velocities. So I could say, well, the second crate's heading down with a negative velocity, the first crate's heading up. But of course, that doesn't really matter for kinetic energy because you're going to square them. Technically, this is what I would say. I would say, due to the rope, I would say V1 final equals negative V2 final. That's what I would say as vectors. And if that's true for the vectors, then when you square them, the squares are the same. So overall, 88.2 can be kind of set equal to, you could just make this a common velocity variable. Maybe I'll just call these both VF. And you add them together, half of 15 plus half of 20, and that's whatever that is, 17.5. And you solve, and I think it would be 88.2 joules equals 17.5 kilograms times VF squared. Divide and take a square root, and this is what I got for final answer is, because of the rope, the two crates have opposite velocities and equal speeds. V2F, when I take a square root, I should consider plus or minus. So I'm going to say the final velocity is plus or minus the square root of 5.04, so it's plus or minus 2.24. Do I want to choose the plus for the heavy crate, or do I want to choose the negative? I guess I'd say it's negative for the heavy crate if you care about directions, and positive for the lightweight crate if you care about directions. I think the question asked how fast, so you could probably, if you'd said 2.24 meters per second, that'd be fine. And I have followed up here at the bottom of the the bottom of the PDF by just saying, okay, the total KE is 88.2. How much of that was in the lightweight crate? How much of that was in the heavy crate? Together, they share the 88.2, but of course, they don't share it equally because one's heavier. So the heavy crate gets 50.4 joules of KE. The lightweight crate gets 37.8. Is that right? Yeah, 37.8 joules of KE. I'm going to do one last thing. Although we've pretty much nailed that problem, I think we've described it pretty well. I'm going to do one last summary of this question. Okay. I'm going to list the 4 key types of energy: K1, K2, U1, U2. Wish I'd gone a little higher. Nah, go a little higher. U2, U1, K2, K1. And then I'm just going to say initial and final. Okay, what happened to K1? It started out at 0, and it started out at 0. K1 ended up at 37.8 joules. That's written at the bottom of the PDF. And this one ended up at 50.4 joules. And then the other ones are, I just want to get the numbers before I leave this view. Okay. What happened to the PE of the lightweight block? It started out at a small height of 1.2 and ended up at 1.8. So it went from 176.4 and it ended up at 441.0. And last but not least, this guy ended up at the ground, but he started out pretty high. He started out at 352.8. I think this is a good summary. How do you guys feel about this? What happened to the KE of the first block? Did it increase, decrease, or stay the same? This one went up 37.8. This one went up 50.4. This one went up. I guess I don't have the number written, but if you subtract those, you can see how much it went up. And this one went up 264.6 joules. And what about the potential energy of the heavy crate? Potential energy of the heavy crate went down 352.8 joules. So this is a pretty good overview of the problem. I have 4 types of energy. One of them decreased a lot, and the other 3 got some of the energy. Some of the energy from the heavy crate going down was able to lift the lightweight crate. Some of the energy from the heavy crate going down sped up the lightweight crate, which is different than lifting it. You could lift something at a steady low speed, or you could lift it and have it accelerate. And the remainder of the energy from the heavy crate sped up the heavy crate. The remainder of the potential energy of the heavy crate sped up the heavy crate. Here's one last question. Would it be true or false? Would it be correct or incorrect to say that the kinetic energy of crate, starting over. Would it be correct or incorrect to say that the mechanical energy of the first crate was conserved? Is 0 plus 176.4 the same as 37.8 plus 441.0? Clearly not. Would it be correct or incorrect to say the mechanical energy of crate 2 was conserved? Incorrect. But it's correct to say the mechanical energy of the combined 2 crate system is conserved. If we go to the view here, how many forces would you put in the free body diagram of the lightweight crate? How many forces in the free body diagram of the lightweight crate and heavy crate as well? Gravity down for the lightweight crate, tension up. Which one wins for the lightweight crate? Tension wins. What about the heavy crate? Gravity down, tension up. Which one wins for the heavy crate? Gravity down wins for the heavy crate. Are there any non-conservative forces acting on the lightweight crate? Normal force doesn't matter, it's not in the problem. Friction doesn't matter, it's not in the problem. Problem said to ignore air resistance, so there's no air resistance, but there's a rope. A rope attached to something I would call a non-conservative force. The book's author would say external work is being done on the small crate, and I would say the same thing. I would say work is being done by tension on the small crate. And work is also being done by tension on the heavy crate. Which way does tension point for the light crate? Up. Which way does the light crate move? Up. That's positive work for the lightweight crate. And we see that its total mechanical energy has gone up quite a bit if you look at the summary. So what allowed this crate's energy to change? The rope. The rope pulled it up and pumped more energy into the lightweight crate. But ropes don't have energy available to them. They have to get the energy from somewhere. So guess where the rope got the energy? It dumped energy into this side of the rope, but it took energy out of this side of the rope because over here, tension was up, but the object moved down. And if you did a work calculation for upward force, downward motion, that's a negative work. So tension did negative work on the heavy crate, positive work on the light crate, and overall we would say the rope transferred energy to the small crate. And this is all kind of, the numbers are here in the summary. All right. I think that is, you should really kind of understand most of the steps there. You will get the wrong answer if you assume that crate 1 has its energy conserved. You will get the wrong answer if you assume crate 2 has its energy conserved. And you will get the wrong answer if you find the kinetic energy and give all the kinetic energy to one of the 2 crates. You have to share the kinetic energy. It's a total of 88.2, but they have to split it. And do they split it equally? They're different size objects. They probably don't split it equally. All right. I'm now going to bring up a question that has something in common with this question. It's going to be a question with 2 blocks. It's going to be a question with a rope. It's going to be a question where both objects start at rest and then they're released. and there's going to be a twist. There's going to be something different about the new problem than the current problem. Let's see here. Okay, there is this problem, and energy worksheet 2 for April 1st. Here is another problem. When released, which block will descend and how fast will it be moving when it hits the floor? We're not going to do this problem fully. We are going to take it far enough to answer the question, which block will descend? And we will, I mean, I think you can, anyways, we'll figure out which block descends. And we'll do some calculations involving energy to determine that. We want to explain our answer not in terms of just our intuition about the problem. We don't want to explain our answer just in terms of free body diagrams. We'd like to explain our answer in terms of potential energy and kinetic energy. So I'm calling this state A. Nothing is moving in state A. 80 kilograms is at this height, and bigger guys at this height. In contrast to state A, here are two possibilities. Call the original or above scenario A and compare it to the two possibilities where each block is on the floor. Do we end up in state B with the 100 kilogram block descending and hitting the floor, or do we end up in state C with the 80 kilogram block descending and hitting the floor? Maybe take a little bit of time to think about that. You got two masses given in the problem. You have two initial heights given in the problem. I would say for the next couple minutes, the initial heights aren't the most important thing. We could figure out which one descends and which one ascends without digging into the exact height of the ascent or the exact height of the descent. And you're also given the sketch of like the pulley system. And I've tried to draw this fairly accurately. So it goes up over a good pulley, down over a pulley anchored to the big 100 kilogram guy. So first of all, let's just kind of go to the chat. I'm just going to ask, which one do you think goes down? If you release these guys from rest, does 100 go down or does 80 go down? While you're thinking about that, does the 100 go down or does the 80 go down? I'm going to show you something that I was going to show you guys the other day. You'll see you'll know when you see it. It's not very important. Here's something I did over the weekend to be a little productive. Picking this up here. Speaking of gravity, speaking of staying inside and not going many places, I have this Lego set. This is the, I don't know if you can see that there. This is the lunar lander from Apollo 11, 50 years ago now, 51-ish years ago. And I kind of dinked around on that. I bought this a couple months ago thinking I would make it with nieces and nephews, and it never quite worked out time-wise. And now that we can't really, go to people's houses and do things like that, I was like, okay, I'm getting it out. It was enjoyable. I will pretend it had something to do with physics when, of course, it didn't. All right. I'll erase this here. Let's see. Place your bets. Place your bets. Does the 100 kilogram block with the double rope thingy go down, or does the 80 kilogram rope with the or does the 80 kilogram block with the single rope go down? 100 kilogram goes down, 80 kilogram goes down. I'm hearing some 80 kilograms goes down. I'm seeing a bunch of 80s. Can maybe somebody that said 80 maybe unmute your microphone and say how you would explain to somebody that thought otherwise or doesn't get it why the 80 kilogram guy goes down? It is the case that the 80 kilogram block will descend. We're going to do a couple calculations to explain that from the perspective of chapter 10 and 11. But how would you explain that to somebody who's like, but I don't get it. 100's bigger than 80.
I think it's because there's two tensions on the 100. So there's two forces pulling up, and on the 80, there's just one pulling up.
That's clearly mechanical efficiency of the pulley system, and I think Thomas referred to mechanical energy. That's kind of mechanical efficiency. That's kind of like a 2-to-1 ratio, and that's kind of what Titus was saying on the audio: 2 ropes and 1 rope. The tip, if you did 100 kilograms and 50 kilograms, it would pretty much be you'd release the system and it would just sit there. They would balance in midair and just either barely move or just hang there. And 80 is going to go down. I'm now going to say, here's how I would explain that to somebody if they are pretty good at thinking about potential energy and kinetic energy. Okay, let's calculate some energies. What is the initial kinetic energy of this object? 0 and 0. Now let's find the initial potential energy. So I want you guys to calculate what is the potential energy of the system in state A, and what is the potential energy of the system in state B, and what is the potential energy of the system in state C. And I don't know if those numbers are at the bottom of the screen. They are not. Okay. I got them written down over here, but they are not on the PDF. So the numbers I'm about to write up, you probably want to write down because they're not in the PDF on Moodle. Okay. UG1, U1 initial, I'm going to say number 1 is 80 kilograms, number 2 is 100 kilograms. U2 initial. So how much energy do we get for an 80 kilogram guy to be, what was the starting height? 2.4. Okay, 2.4. I don't think my picture is to scale, but we'll go with it. 80 kilograms times 9.80 times 2.4. 1,881.6 joules. And 100 kilograms was only at a height of 1 meter. And that is only 980.0 joules. So I'm going to say total potential energy initial. And I'm going to add those up. 2861.6 joules. And now this is, I meant to call this A, not initial. Same idea, I just want to call it A. Okay, let's redo this for B. I'm gonna keep this number at the bottom for safekeeping. And I'm gonna put UB right here, and I'm gonna put UC right here. When I get there. Okay, what is state B? Now, you guys basically just told me, a bunch of you guys said correctly, we're not actually going to end up in state B. We're going to end up in state C, but I'm still going to calculate some numbers for state B just to help me understand the situation. What is the potential energy of the 100 kilogram block in state B? So I'm going to go to B, and state B is the 100 kilogram block ends up on the ground. No potential energy. This is 100 kg, and this is 80 kilograms. What about the final height of the 80 kilogram block? This is the tricky part of the problem. How high would the 80 kilogram block end up if the 100 kilogram block ever ended up at the floor? So how far down did the 100 kilogram block go? It went down 1 meter. How high will the 80 kilogram block rise when the 100 kilogram block goes down 1 meter? Because of the rope, because of the mechanical efficiency that Thomas referred to and the 2-to-1 ratio on the ropes that Titus referred to, when this block goes down 1 meter, This rope section gets 1 meter longer. This rope section gets 1 meter longer. So this rope section gets shorter by 2 meters. And so what's the final height of the 80 kilogram guy? 4.4 meters. And if he ends up at 4.4 meters, I'm now going to calculate potential energy. And, oh, I was too fast on the mouse. He's going to end up at 4.4 meters, yeah, up 2 meters, like Dylan said, from where he was, for a total of 4.4. And his potential energy has gone up a lot. We just lifted an 80 kilogram block 2 meters. Okay, so what is the potential energy of state B? All the stuff up here right now is B. Just add up 0, and that's not a big deal. 3,449.6 joules. Can the system go from A to B? One more thing I want to say. What's the kinetic energy in state A? No motion. So there was zero potential. There was zero kinetic energy in state A. We don't have enough energy to get to state B. Do you see that? In order to get to state B, what would have to happen to the kinetic energy? The potential energy went up from 2,800 to 3,400. The kinetic energy would have to go down about 600 joules, but the kinetic energy can never go below 0. Potential energy can be positive, 0, or negative. Kinetic energy can only be positive or 0. So this is impossible to do from the point of view of energy conservation. In order to get to state B, somebody needs to input more energy to the 2 crate system. Somebody needs to take the rope and like hand over hand pull on the rope or do something like that. And if that's not occurring, we can't get to state B. Let's just go back and calculate potential energy for state C. Go ahead and work out potential energy of state C. Final height of the 80 kilogram guy is 0. He's on the floor. So the number 1 crate in state C ends up at 0. Easy. How high does the 100 kilogram crate end up in state C? When 80 descends 2.4 meters, the 100 kilogram guy moves in the opposite direction half as far. So the 100 kilogram guy only rises 1.2 meters. And if he rises 1.2 meters, he will end up at 2.2 meters. So let me try this here. Oh, gosh, some stuff's in the way. So let's see, what do I get? So we have a 100 kilogram crate. Gravity is 9.80, and he ended up at the starting height of 1 plus half of the rise, half of the height change of the 80 kilogram crate, and I ended up with 2156. So here we go. This is going to be doable because the total potential energy in state C is 2,156 joules. Keep on doing that. I don't know if you guys can see that. Hopefully you can. So can we get from A to C? Yes, we can. In terms of potential energy, which way does a system want to move? Does it want to move from 2,800 to 3,400? Or does it want to move from 2,800 to 2,100? A system will always move, if left to its own devices, if nobody's got a hand on the rope or anything like that, a system will always move in the direction of decreasing potential energy. A free system, I'm typing something in the chat, a free system will want to move in the direction of decreasing the PE and thus increasing the KE. kinetic energy. Okay, a free system will want to move in the direction of decreasing the potential energy, even if it has to lift an object. Like we're lifting the 100-kilogram object, but that's still the preferable energetic direction because it decreases the potential energy. I'll leave the problem there. What would I do to finish it off? I would say I would look at the change in potential energy, and whatever amount potential energy goes down, that's how much kinetic goes up. And what would the final part of the problem be? It'd be to figure out how to share the kinetic energy between the two objects. And I'll just say in the sidebar, V1, let me say this, V2, and that's the 100-kilogram object, equals negative 1/2 times V1. That is because the rope is attached. When object 1 goes up 1 meter, object 2 goes down 1/2 meter. So if you kind of use this substitution, you could figure out the final speed of both objects. And of course, the upward heading guy is going to be going at twice the speed upward. Sorry, I said that wrong. Anyways, it's written on the screen right. I was just gesturing on. The 80-kilogram guy goes down and hits the ground heading fast. He hits the ground heading twice as fast as the 100-kilogram guy is moving upward. And that's that mechanical efficiency or mechanical advantage ratio of 2 to 1 coming out. So you could explain it in terms of like 2 ropes is double the tension, which is kind of a force chapter 5, 6, 7 way of talking about it. Or you could talk about it as one guy changes height twice as much as the other guy, and that requires twice as much PE to change height that much. Okay. Well, I don't think I'll really start in on anything else. We got 4 minutes left in class, so won't do that. Could I just ask a couple questions? How well can you guys see the board? Because I don't really know. I mean, I kind of know, but I don't really know. Awful, medium, terrible, okay. Okay, I keep trying different spots in my apartment, and even the time of day makes a difference. Like in the afternoon, the light's kind of different and things get kind of glary. I think you can make stuff out, but it isn't great. Yeah. I'll work on getting a 4K ultra camera. I don't got one of those at the moment. All right, last question. I'll leave you with this. Oh, we have lab tomorrow. What's the lab going to be? I'm trying to remember. I'll tell you about it. I'll tell you about it a little bit more, maybe in an email before lab. There might be some equipment that would be good to have. Okay, let me mention this instead. I don't know if this is quite going to happen by tomorrow's lab. Okay. I don't know if this is quite going to happen by tomorrow's lab, but one of the upcoming labs, I'm hoping to do a lab that I'm hoping to do a lab soon. Yeah, I'll address that, guys, about the lab. Yeah, you don't need to just turn in the lab in until end of the day Thursday to address that. I'm hoping to do a lab soon, if not tomorrow, maybe a week from tomorrow, where you would have some cardboard. I'm imagining just any kind of, okay, yeah, Thursday. If you had like a shoebox or something like that, if you had some cardboard available that you could cut out into various shapes, maybe I'll just grab some pieces and I'll kind of show you what I have in mind just to put it in the back of your head and maybe keep your eye out for something like that you could collect for either tomorrow or more so a week from tomorrow. Give me a minute. Okay, so let me just kind of hold this up here. So like here, somebody cut a semicircle out of cardboard and then they made some markings on it. It's just a thin little piece of cardboard. We also did, you can see this, like an L shape piece of cardboard and a piece of paper for kind of attaching it to things. So I'd like to do something like this at some point in the future. Here's a quadrilateral. Here's a quadrilateral. Just a little piece of cardboard, or maybe an object with a hole in it. A nice circle with a hole in it. So maybe we're going to use something like this. If you could spot something like this around your house, maybe set it aside, and we will use it at some point in a lab on Thursday. Okay, thanks for listening, everybody. Have a good day, and I'll see half of you at whatever time lab is, 10:50 tomorrow, and the other half of you, I think 12:45 tomorrow. Have a good one. You are remotely dismissed.
Have a good rest of the day, Professor.
Thanks.